All right, so today we're going to be talking about Shannon's noiseless coding theorem. So keep in mind the example of encoding text using a Huffman code throughout this, because the Huffman code is one example of where we achieve the best possible behavior predicted by Shannon's theorem. So our goal, remember this for Huffman codes, is to minimize the average length of encoded characters. So that's going to mean that the overall text, once we encode it, has the shortest length. And so we kind of measure that based on the average length for characters, is going to give a similar measure for that. And then so we've worked that out by doing the sum of adding up the relative frequency of each character times the length of the encoded character. So this will be easier to see working out with an example what this actually means. So that's what we'll do. So here we're looking at this example that we saw in the pre-lecture from Monday, where we built a Huffman tree for the characters A, B, C, D with these probabilities. So if probability of A is 1/2, probability of B is 1/4, probability of C is 1/8, and probability of D is 1/8. So we're going to start by writing down the lengths of the string of digits when these letters are encoded. So when we encode A, that's encoded as just 1, so our length there is 1. For B, B gets encoded as 0, 1, so our length there is 2. For C, that's encoded as 0, 0, 0, so that has length 3. For D, that's encoded as 0, 0, 1, so that has length 3 as well. So figuring out the average length F, we work that out as adding together each probability times the length. So 1/2 times 1 plus 1/4 times 2 plus 1/8 times 3 plus 1/8 times 3. And this works out to be 7/4. So we get 7/4 for our average length there. Now let's look at this for the same probabilities, but now look at the encoding of these letters according to this tree below. So we know that from our Huffman tree construction that this one was not as efficient, and we'll see that when we compute the average word length. So our word length for A here is 2. For B, 2, C, 2, and D, 2. So then when we're adding up the, to find the average length, we're doing 1/2 times 2 plus 1/4 times 2 plus 1/8 times 2 plus 1/8 times 2. So for this one, we get 2. So here we see that the average word length here is 2, and the average length for the first tree for that Huffman code was 7/4, so we can see by that measure the first encoding is more efficient, like we had expected based on what we were trying to figure out with Huffman codes. So we've talked about how Huffman codes give the most efficient way to encode characters in strings of digits based on their frequencies. And Shannon's theorem sort of makes this more precise. We say what we mean by things being efficient, give a bound on that efficiency, which then tells us that the Huffman codes are in fact the most efficient. So for any binary prefix code encoding the characters x1 up through xm, the average length must be greater than the entropy of the source. So when we're looking at these letters and their frequencies and computing the entropy of that stream, then that entropy is going to be less than or equal to the average length of the encoded words, that thing that we've just been computing. So in addition to saying that this average length is at least as big as the entropy, we also know by this theorem that there exists a code such that the average length is less than 1 plus the entropy. So this means that we can get really close to that bound. We can get within 1 of that bound, and there will be some code that gets that close to that bound given by the entropy. So going back to our example that we were looking at with the Huffman code for these letters with these probabilities, we computed our average length to be 7/4, and our entropy here is minus 1/2 log base 2 of 1/2 plus 1/4 log base 2 of 1/4 plus 1/8 log base 2 of 1/8 plus 1/8 log base 2 of 1/8. So working this out, this actually comes out to 7/4. So we see that in this case, that average word length matches exactly that entropy. So certainly this is the most efficient way to encode those letters. And Shannon's noiseless coding theorem tells us that it's impossible that any code could do better than this. So the Huffman code is in fact optimal. So a few notes here. By the previous theorem, it's possible to show that Huffman codes are optimal. So we sort of saw that demonstrated by that example, but it's also possible to formally prove this. So this is proven in the text if you want to look at that, or you can find other sources which prove that Huffman codes are optimal when we consider them with that measure. The book generalizes this to codes that aren't just going to zeros and ones, so codes that aren't just binary. So you might see the theorem looking a little bit different in the book because of that. There's a divided by log factor that comes in because we're encoding things in potentially more than just 2 characters. So that's a generalization of the Shannon's theorem that we gave in this video. And remember here, we are still assuming that there are no errors, so we're only talking about noiseless coding here. So noiseless coding means we're assuming there are no errors. So everything is being transmitted perfectly, and we're trying to then compress data or encode things in the most efficient way possible, which we can do with Huffman codes. But like we saw in the first lecture, there's a trade-off there where by making this so efficient, now if there are errors in this, it's really hard to read a Huffman code. So this is great when there are no errors, but if there are going to be some errors, then this Huffman code really breaks down. So this is really only applies to noiseless coding where there are no errors in transmission.